about the exponent of distribution for the divisor function, the ordinary divisor function. Okay, so if you recall from last week, I defined two notions of exponent of distribution. There's the strong one, and there's the other one that is the one that comes up in the Bombieri-Vinogradov theorem. So today I will just deal with tau 2, which has, and with the strong exponent of distribution. So I will just recall the definition of that strong exponent of distribution. And tomorrow I will explain more about the bilinear form methods that come up in trying to prove estimates for exponents of distribution for primes and related functions, in which case we'll go back to the Bombieri-Vinogradov type definition. So this is just a reminder of the definition, and I'll just specialize to the function which we are interested in the second part. So f is the ordinary divisor function. Then there's the discrepancy where I don't put the tau 2 since it's fixed, which is just comparing the values of the divisor function in some interval restricted to an arithmetic progression, minus something which we feel should be the average of the same quantity over the residue class, and the residue class is taken to be a primitive one, modulo q, so that this sum is over n coprime with q, and then one expects that these are well distributed, so that this should be close to this quantity for every a. So delta should be small, and the goal of today's lecture is to explain the proof of this theorem, which is due. So I don't know who noticed this first, but alphabetical order, it seems to have been observed at least by Uli, Linik, and Selberg in the 60s, and which states that, so I'm going to state it as an estimate and then deduce what it means in terms of exponents of distribution. So it's a straight estimate uniform in x, q, and a, and it really takes the form x to the epsilon times square root of q for all, let's say x at least 1, q at least 1, a coprime is q. There's an implied constant in the Vinogradov symbol, but it depends only on epsilon. Okay, so what it means concretely in terms of exponent of distribution. So when is that telling you what we want for an exponent of distribution? So the question is, when is this remainder term, this error term, smaller than what we expect? So recall that what we expect is something of the size x over q divided by an arbitrary power of log x, I should say phi of q. Right, so this is more or less phi of q is essentially q, so you want q to the 3/2 to be of size a little bit less than x, which means q of size a little bit less than q to the 2/3. So this theorem means that the strong exponent of distribution of the ordinary divisor function, well, it means that 2/3 is a strong exponent of distribution. Yeah, sorry. Here, that's minus epsilon. There's actually not. Yeah. Okay, and this can be made more precise. The x to the epsilon could be some power of log x, so you could actually say something like q up to x to the 2/3 divided by some fixed specific power of log x if you want to gain a log x to the. Like in the Bombieri-Vinogradov theorem, you sum up to square root of x divided by some power of log x. It depends on what you want to gain on the right-hand side, and one can be very precise on what is the upper bound in terms of the a that you want. But in application, this turns out to usually be completely irrelevant. It's usually either the thing here minus epsilon works, or anyway, it's no good for applications. So I won't bother trying to be much more precise than that. Okay, so let's see how the proof goes. So I'll first recall very briefly how we sketch the fact that the exponent of distribution could be taken to be 1/2 for this ordinary divisor function. So it was this very simple-minded application directly of the definition and the Dirichlet hyperbola trick. So it's approximately the sum over to square root of x, and then there's a sum over an interval of just the ordinary function 1, and then one tries to replace this by main term plus error term. Okay, and if you do this, you cannot go beyond an error term of square root of x, which gives you just x to the 1/2 as exponent of the level of distribution. So here you can see that the type of problem that arises is similar to the one that arises when trying to apply very simple-minded sieve and inclusion-exclusion to prove the prime number theorem. So there's a main term that looks reasonable enough, but the error term, just the straight sum of the error term is too big. So you need to detect some cancellation in the sum over m of these big O of 1s. So to go below or beyond q less than x to the 1/2, one needs somehow to understand, to some extent, the big O of 1. Okay, and its variation with m. So we're in a better situation than in the case of the prime number theorem, because here in that case, the main term is not lying. So if you just sum the main term, you get the right main term. Okay? In the prime number theorem, if you just apply sieve and inclusion-exclusion, the really significant issue is that if you just trust the main term, it's giving you the wrong constant in the asymptotic. So we have tools to handle such situations, and they're all based on harmonic analysis, or at least those I understand and know are based on harmonic analysis. So we want to replace this sum by a combination of other terms where the main term is very clear. So whatever is the x over mq will come very naturally, but instead of just plus big O of 1, you'll have some other things, then you just try to manipulate that afterwards. So the idea is to use harmonic analysis and it's a common idea that, for instance, the proof of Dirichlet's theorem on primes in arithmetic progression is based also on the same idea, that you want to detect that the primes are well distributed in all progressions, and you decompose the characteristic function of the given residue class in terms of Dirichlet characters, and then there's the trivial character. The principal character tells you what's the main term in a very natural way, and the others have to be handled to understand the error term. So to replace big O of 1 by analytically accessible expressions. By which I mean, of course, you could say this is just some kind of fractional part of something, but usually if you just write a fractional part of something a bit complicated, this is not much more used than just writing big O of 1. It doesn't tell you that much. You need to go a little bit beyond. So the first idea would be to expand in Fourier series the fractional part symbol. That certainly is doable. What I'm going to do will be slightly different. I'm going to use a more symmetric approach because it generalizes better and it avoids viewing the factorization of n as a times b, which is what we have to count in the divisor function. We're going to treat a and b more symmetrically than with the hyperbola method. Okay, so we use a more symmetric approach, but it certainly is the same idea. Okay, then Dirichlet. So more generally, I will describe the general tool because it has many more applications than just this one. And instead of just viewing this tau2 of n congruent to a mod q, I'm going to look at situations where we are working in z to the k. So k is some fixed integer that in our application will be 2. So n is a vector with k components which are integers. And we're going to have some kind of a nice smooth function which I will call v and not f. So it's a function of n variable defined on Rn, or Rk, sorry, and with very good decay properties. So you can think compactly supported, or you could take it in the Schwarz space, which is a bit more symmetric sometimes. So if you've never seen the Schwarz space yet in your studies, just think compactly supported. It certainly doesn't make much of a difference. Okay, so Schwarz space means decays faster than any polynomial at infinity, and all the derivatives also decay faster than any polynomial at infinity. Okay, so this you have to think of as a smoother version of the characteristic function of an interval or of a box. And then we're going to have some arithmetic factor k, which is going to be periodic modulo some integer q. So it's a function now really from z mod qz to the power k for some modulus q that we view as a function on all of z to the power k by just composing with the natural projection. So we want to look at such sums because they are, in certain parts of analytic number theory and of number theory more generally, there are certainly sums which come up all the time. So in our example, so maybe it doesn't quite look like this, because so if you just try and do it naturally with k equals 1, you would take, say, maybe v to be an approximation of the characteristic function of the interval. But then tau2 cannot be of the form k because it's not periodic. However, if you write our sum by explaining what is tau2, so it's just a convolution of 1 with 1. So this will be the sum over AB such that the product is less than x. Okay, A is very not. I'm going to reuse M and N as variables. So N is not the same as before. So we view this as a sum with two variables M and M. So V is the characteristic function of this condition. So M and N are at least 1, so it's let me call M and N these variables. So Mn is equal to x describes the hyperbola, and we're looking at the parts of R2 in the upper quadrant below this hyperbola. So it's a characteristic function of this set. And K of Mn is periodic of period Q. It's just the characteristic function of the congruence class Mn is equal to A modulo Q. So you take M and N, you reduce both modulo Q, and you compute the product, and you check whether it's equal to the given residue class mod Q. So it comes up in this form when you do this operation, except that formally it's of this form, but as soon as you give conditions on V, it's not of this form anymore, because this is certainly not, this characteristic function is certainly not analytically extremely nice. It fails both to be compactly supported and to decay at infinity. So part of the work, which is very standard, it will be to replace this function, which is literally what comes up in the formula, by something analytically better behaved. Okay, but at least formally, if we know how to handle very general sums of this type, this will apply in this problem. So I'm going to first concentrate on the smooth version and state the formula which transforms this into something different, which is often more manageable. Okay, so at first I'll state a formula. So formula is just an identity, and it's always valid. And then we'll see a little bit analytically what the formula means and why sometimes it's a formula that you should apply and sometimes it's a formula that you should not apply, because analytically either it transforms a problem that's hard into something easier, or it could actually transform something easier into something harder. But let's start with the formula, which is just the Poisson summation formula. Very slightly generalized compared to what sometimes is stated in books. So I presume that many of you have already seen this formula. I will state it anyway and explain how it's proved quickly. So with the same notation as before, so we have the following expression. So we start with the original sum with the same conventions, and we're going to replace it with a different sum where, roughly speaking, V is replaced by its Fourier transform and K by its discrete Fourier transform. Okay, so it makes sense if you think of the Plancherel formula. You have two functions, and usually you can replace a nice average of a product of two functions by the same average, but for the products of Fourier transforms. Okay, and we just have to be a little bit careful with normalizations as usual. So the way it comes out, the way I want to do it, there'll be a normalizing factor 1 over Q to the K over 2, sum over the dual variables coming up in the Fourier transform, which I call H. So it's again in ZK. Then we'll have the Fourier transform of V. I will recall the normalization I use at H over Q. Okay, so H is a vector, and you divide every component by Q. And then you have the Fourier transform of K at H. So a formula like this is not surprising, but we need to explain the normalizations. So V hat is defined on Rk again into C is V hat of T is integral over Rk of V of x E of minus inner product of x with T dx. So standard Lebesgue measure, that's the exponential 2i pi z, and that's the standard inner product sum of xi ti. And so the Fourier transform, the discrete one for k, is 1 over q to the k over 2 times the sum over x in z modulo qz to the power k, k of x, e of x inner product with h over q. Okay, so note the normalization are a bit inconsistent, because here I put a minus, but here I did not. That's partly based on history. It has the advantage that there's no complex conjugate in the Poisson summation formula. That's cosmetic, but just in case you compare with other formulas in the literature, sometimes they would be complex conjugates, but that depends on the way you normalize various Fourier transforms. And the choice of normalization of the Fourier transform in the discrete case is so that the Fourier transformation is an isometry for the standard inner product, which is the average of functions on Z mod QZ to the power K. And we'll see also a little bit later why this is a good normalization. It's compatible with the square root cancellation philosophy that will tell you that if you start with a bounded function and it's really well behaved, then the Fourier transform will also be bounded, which is the type of thing that makes some heuristic arguments much easier to remember. Okay, so it's an identity. If you were to take Q equals 1, you would get the really completely standard Poisson summation formula, which is completely symmetric. And if you apply it twice, you just back to the original thing. And if Q is larger, it gives you a way of generalizing these things. Okay. So let me just give an idea of the proof. I mean, I presume this is something that many of you are already familiar with, and this is not very hard. So basic ideas you consider. Okay, so first you split into congruence classes. To use the fact that K is periodic, so it's going to be the sum over A in Z mod QZ to the power K, K of A, and then the sum over, so V congruent to A modulo Q, which you can replace by a free summation over M of A plus Q times M. So you have to view A as a vector of integers, but that's no problem. And then this is a case of the standard Poisson summation formula. Okay. So the way to handle the standard Poisson summation formula is to consider a function of y, which is the sum of v of a plus qm e of m inner product with y. So it's a sum of m in zk. So because v is assumed to have good decay at infinity, this is a function which is well defined, and because we're averaging over the integer lattice, it's in fact periodic of period 1 in each variables. So you can expand in Fourier series. K variable Fourier series. And the Fourier coefficients turn out to give you more or less the Fourier transforms at H over Q. So Fourier coefficients. So because of the shift, there's going to be an exponential that comes up, which will probably be, okay, let me put an A inner product with H over Q. So the Fourier series expansion will be the sum over H of this times E of AH over Q times E of XY over Q. And now if you apply a change of order of summation, in this case you'll get the K of A times this, which is the Fourier transform of K, and the VA at. And you just have to be careful that the normalization comes out right. Okay, so I won't say more, but this is an easy exercise worth doing at least once if you've never done it. Okay, so that's an identity. It's essentially an involuntary identity in the sense that in the case Q equals 1, you apply it once, it gives you something else. You apply it twice, it gives you back to where you were. In the case where V is in the Schwarz space, it's completely symmetric because V hat is also in the Schwarz space. When V is compactly supported, it's not quite true. V hat cannot be compactly supported if V is non-zero, but it still will be decaying very fast at infinity, which is what I'm going to check now, because now I'm going to try and interpret this in a more analytic way to understand a bit what it means intuitively if you want to apply this formula to a really analytic number theory problem. When is it good to apply it? When is it bad to apply it? Okay. So to do this, I'll do it in the case k equals 1. So in analytic problems, so V is typically approximation to a characteristic function of some interval. So let's say it's about characteristic function of an interval of length y. But it's still smooth. So it's something like, might as well use some of this chalk at some point. Okay, where the length here is roughly y. Okay, and what does it mean to be a good approximation of a characteristic function of interval of length y? It doesn't only mean that it looks roughly like this. The derivatives also have to be compatible with the type of thing that you want. So the picture to have is, so on an interval of length y, maybe it's identically 1, and then it decays from 1 to 0 or starts from 0 to 1 on intervals also of length comparable with y, maybe y over 2 or whatever. And so now we need to have bounds on the derivative. So now there's just one variable. So what are the bounds on the derivative that you will expect? So with some constant that will depend on the order of the derivative. Well, for the first, well, the zeroth derivative is just bounded by 1. The first derivative, as I said, if we think that maybe here this is of length y over 2, so it has to go from 0 to 1, and it has a space y over 2 to do it. So average derivative would be something like 1 over y. And of course, it could be oscillating much more than that and have much higher derivatives. But certainly, if it was just a piecewise linear function going from 0 to 1, the derivative would be 2 over y. So we want something that's comparable with that. And if you draw the graph of the derivative, well, it will be 0 at many places if it's really identically 1 on this interval. But apart from that, it will have two peaks that look a little bit like this. But now it will only have time y over 2 to go from 0 to 1 over y. So which means that the second derivative will be typically of size 1 over y squared. Okay, and you iterate this by induction. So you would expect that this should be a reasonable approximation. Okay? And it's not difficult to really construct functions exactly with this property. So they're very close to the characteristic function of an interval of length y. They're exactly equal to 1 on this interval, and they are 0 outside of some boundary things of size, let's say, y over 2, and the derivatives satisfy this bound for every j. So let's assume that V is of this type. So then the left-hand side in the Poisson summation formula is something that looks a lot like the sum over that interval of length y, but congruent, no, sorry, I didn't put the congruence class, I have this general function k. Okay. And now we're going to try and interpret the right-hand side in a similar manner. So I'm going to state what it looks like, and then I'll justify it. I think this might be clear. So the right-hand side will be approximately, okay, I have to make it correct. So the sum over h bounded by q over y of the Fourier transform at h. Okay. So, and here I'm going to normalize like that. So, because that's the way that I remember it best. And I have to tell you a bit what this squiggle means. So it's not a meaning of squiggle that you've yet seen, at least in these lectures. It's slightly different. Okay. But so the way I remember it myself, at least, we sum over an interval of length y a q periodic function. We normalize by square root of y with the idea that k is oscillatory and there should be square root cancellation. So if there's square root cancellation, this should be a bounded quantity to some extent. And the sum is replaced by a sum of the Fourier transform. The length of the interval goes from y to q over y. So the product of the lengths is constant. And when it's normalized in the same manner that compatible with square root cancellation, we have something that looks very much the same. So we'll see how to use that. So this is, of course, if you apply this, as you will see, in no way do you get a rigorous proof of anything. But you get something that's extremely robust and certainly will tell you with 99% chance of success whether whatever approach you have in mind for a problem has a chance of succeeding or not. I mean, it could be that there are really subtleties in this squiggle sign, but typically, if this heuristic, as I'm going to use it, tells you you're going to fail badly, you really are going to fail pretty badly. Because you would really need to do something that's really unusual to still have a chance to succeed. So let's see why this is, what this squiggle means and why this is reasonable. Okay, so we have the function v is well defined. It's an approximation to this characteristic function. And I apply the Poisson summation formula. This is still an identity. So k is equal to 1. So it looks like this. Okay? So h is in z. So what I need to understand, if I claim that this is really more or less a sum of an interval of length q over y, I have to estimate this and check that it doesn't exist essentially beyond such a bound. So what's the Fourier transform? We can bound it for every t. And we just bound it in the most naive way imaginable for this type of things by successive integration by parts. So that's the gain in having a smooth function. You can integrate by parts. Every time you integrate by parts, you're going to get a 1 over t coming up. And then, so if you do it many times, you get a decay, a polynomial decay of arbitrary power at infinity, which is exactly how you would prove that this is a Schwarz function. Except we're going to do it in a slightly more precise way because we want to have more quantitative estimates than just saying it's a Schwarz function. So integrating by parts, maybe if t is non-zero, if you really want to be picky, you get something like that. Because of the minus sign, then you have integration of r, j's derivative, dx, and so next board. Okay, so you get that v hat of t is going to be bounded by up to an absolute constant 1 over t to the j, absolute value. And this integral we bound trivially, so v is concentrated on the interval of length y. And on this interval of length y, it's bounded by 1 over y to the j, so it's y to the 1 minus j. With an implied constant that depends only on j, which I write as y divided by absolute variety times y. Sorry, here I forgot the h over q. Okay? And now we see what happens is that if, let's say y, if t is larger than by even a very small amount. Taking j very large makes it extremely small. So let's say times a huge constant c. Okay? And so this is in this sense that we interpret these properties, these Fourier transform properties of such functions similar to a characteristic function of an interval. We're going to say that the Fourier transform is like the Fourier transform of an interval. Maybe not quite the characteristic function, but it's supported on an interval of length 1 over y. And so that's known also as an instance of the uncertainty principle in harmonic analysis. You want to isolate an interval of length y. And to do this, you need to use Fourier coefficients up to 1 over y. So if you want to make y extremely small to analyze a function extremely close to a single point, then you will need to use all of the Fourier transform, more or less. And there are various ways in which this comes up in many, many places in analysis and in analytic number theory. And what we're doing is one instance of that. So if we apply this to our typical case, okay, so we expect at least that the sum should behave as if you could truncate it to q over y. There's still the V8 of h over q. Okay, so this first use of the squiggle means that you expect that you can handle the cases where h over q is larger than 1 over y, which means h larger than q over y, by kind of trivial estimate using the fact that the Fourier transform is extremely small in such a range. So you typically need to take a little bit more than q over y, maybe q over y times to the power 1 plus of something very small, or q over y times some very large power of log q or something like that. But that's something that works out fine in practice. So it's still not quite of this shape. So the left-hand side, if we interpret v as a characteristic function, is more or less as I wrote down. But here we still have this v hat. So now what can we say about the Fourier transform, again, for t less than 1 over y? So it's integral again. I just write the same as before. Okay, and here the point is, so this is integrating really over an interval of length y. So the initial point of the interval doesn't matter too much. It's just going to be a phase factor of modulus 1. And if we think that this interval, let's say, is absolute value of x less than y over 2, let's say, to have an ID. 1 over 2y, because it's length 1 over y. To a first approximation. Then the point is x times t does not vary too much. It varies in a bounded interval, so the exponential doesn't turn. It does not oscillate. So then the idea is that this is a function that maybe is not like a characteristic function of an interval, but it's a very smooth, non-oscillatory function. And so we view it as more or less the same as having the characteristic function of the interval on which it's supported. Well, times what is its typical size? Because if there's typical size 2, it's not the same as typical size 1. If the typical size is very large, this only will not look like the characteristic function of this interval, but as a multiple, which is a large parameter. So what is the typical size of this? Well, if we think of v as being really flat, there's only no cancellation from this side. Because x times t varies in a very small range, the exponential doesn't oscillate so much either, so there's no cancellation from there. So it's really like integrating the constant function 1, because v is about 1 all the time, or bounded by 1, but over an interval of length y. So, oh, sorry, here again, I got confused. Sorry. It was y, sorry, because it's the support of v. So we're integrating over an interval of size y, a function that's more or less always bounded by 1. So it's something that typical size should be of size y, which is in fact the same y that I erased. Oh, the same y as here. When you take v hat with j equal to 0, you get just y. And that's exactly that y. Except that now I'm arguing that not only is it an upper bound, but really you cannot expect to have something smaller than that. Okay, I think I can use that again. Okay, and now the really meaning of the squiggle is that we're going to pull out this constant, which is the typical size, and we're going to argue that the rest, even if it's not constant, is really like a constant of size 1. So heuristically, so some v of n, k of n, somehow looks like y times the sum over h less than q over y of k out of h. Okay? And here the squiggle means that I'm omitting functions here which are very smooth and non-oscillatory. Okay? And this makes sense from the point of view of going further, because we know that such functions can be handled by integration by parts or summation by parts or similar techniques. So they're usually not a problem at all. Like in Zhang's lecture yesterday, Polya-Vinogradov was sum of chi of n, but it's not difficult then to go to sum of chi of n times log n. And so when we write something like this, we're hiding kind of an arbitrary but very smooth and nice function bounded by 1 as a factor of the k out of h, and then we do the same here. And this was n interval of length y. And again, I forgot the normalization factor, so there was a 1 over square root of q, which I should have left here. So here I still have 1 over square root of q. And so this is certainly, I think, correct, if I didn't make a mistake. Let's check now in the way that I like to check so that I remember it correctly. Let's assume that k is very nicely bounded and oscillatory. So this should be of size about square root of y. So check. So expect typically, certainly if you take the function k at random in any reasonable sense of random, this would be square root of y on the left-hand side. And here we would get y over square root of q times q over y times square root of q over y. So this is a constant. Here again, we assume that typically the Fourier transform will have the same kind of square root cancellation properties. And so let's see if this fits. Yeah. Okay. And if now you divide by square root of y, you will get this more symmetric form that I claimed. So if you divide by square root of y on both sides, you get 1 over square root of q over y. And that's a way of checking that. Okay, so I spent a little bit of time on this because I think these are the kind of heuristic tools that are very important in trying to figure out how to prove certain things, how to make a first guess whether a method has a chance of succeeding before having to go to the really precise details. So I'm now going to start coming back to this divisor function and estimate it following such IDs. Okay, I just need to find the right page. Okay. Okay, so back to the divisor function. Okay, so I'll write again the way I want to think about it. So we have two positive integer variables. And I write k of m and n for the characteristic function of the residue class A for the product. So this is characteristic function of Mn equal A mod Q. Okay, and we want to view this summation condition as inserting a nice smooth function. So the function is certainly a nicely continuously defined function, but as I said, it's not smooth, it's a characteristic function, and it's not well bounded. So we use these ideas of dyadic, or in this case, we'll have to be slightly more precise than dyadic subdivisions. Similar to what Zhang was talking about yesterday, and separation of variables to reduce from this sum, which is formally of the right kind, but analytically does not have the right properties for V, to something better behaved. So intuitively, it looks in the following manner. So to write this sum as a combination of sums of the type, so there's now going to be two independent variables, which formally I will see as living in Z. So the first one will be constrained by some test function to be in some interval of length capital M. And this one to basically be a characteristic function of interval of length capital N. And then K of M and N. So what are the conditions that are involved? So let's draw the picture. It will be clear what happens. I'm not going to give the completely full construction, but it should be relatively clear what I want to do. So I want to first get the variables in smooth intervals, and then I want to separate the variables so that here it's a completely free summation. So this is the last step that Zhang didn't perform in the proof of the Bomberi-Vinogradov theorem yet. So we had this Mn less than or equal to x, and he said one has to take that into account. He will explain again how this is done. So you have to think that we are now summing of such intervals. So we're covering the points of interest, the points in the upper quadrant below this hyperbola by squares or rectangles like that. So it's quite clear that, so Mn must be basically less than or equal to x. You don't want too many intervals because we're going to sum trivially any other term on all these intervals. So the length M and N, so we want no more than about, well, if we want to gain powers of log x, so we should have no more than some power of log x intervals. Okay? So we could certainly cover the whole thing by one interval of length x and another interval of length x, but for the same reason as the trivial linear decomposition yesterday was useless, this would leave you as something that you don't want to take all the upper part of the hyperbola. So we want whatever looks to be on the boundary here, but above the hyperbola to be quite small. We're going to handle that trivially, meaning that we'll bound the contribution of these things by just the number of points. And so we need the length of M and N to be such that whenever we go above the hyperbola, we don't go by more than a power of log x. So we need M n to be say x divided by, well, So the intervals to be of the type you start from something, let's call it alpha, to alpha times 1 plus some power of log x. Okay. So think of alpha as being very close to square root of x, maybe. Then so you go from square root of x to square root of x plus square root of x divided by power of log x. So if you're, let's say, on this diagonal part where m are equal to n are very close to square root of x, this contribution here will trivially be of size at most x over log x to some power. Okay. Just by computing, in fact, the total number of points on this thing. Okay, I can erase the Poisson formula. Okay, so there are standard lemmas in the literature when one really wants to write a paper, but intuitively this is well-established technique, so I'm not going to give more details right now. So we have a combination of such sums. So with Mn close to x. So why can I take Mn close to x? So of course the upper bound is close to x. In fact, also the lower bound can be taken to be quite close to x, simply because if you sum the total number of points a little bit below the hyperbola, then this is within the trivial bound. So you can compute completely trivially the number of points that would have Mn less than or equal to x divided by some really huge power of log x. This will already be good enough. We only want to gain powers of log x. So something like x over log x to some huge power, x maybe times log x, something like that. So m times n is quite close to x, and the rest is end-all trivial. Okay. Now there's one last thing that before I explain the steps and why this leads at least to an intuitive guess that the statement of the theorem of Woolley, Deligne, and Selberg is true. So I'm not going to worry about the main term. Well, I'm going to explain a little bit where it comes from, but I'm going to start by not worrying at all about the main term. I'm going to take one of these sums, a single one of them, and try to bound it from above. Okay? Now, this cannot quite succeed because we know there should be a main term. We really are counting the points under the hyperbola with weights 1. Even if they're congruent to A mod Q, there's many of them, so it has to be large. And if I just give an estimate that's non-trivial, there's something I'm doing wrong. Okay? And we'll see where the something wrong comes in. Now, the last step I won't do is to explain how this something wrong. I will explain that it gives the main term. I will not reconstruct completely the main term from that. It's not actually very hard. You basically have to redo the same thing with Q equal to 1 and check that with Q equal to 1, you get precisely this main term as the main contribution. That it doesn't really depend on A. That's essentially the point. Okay, so we handle one such sum. Yeah, 5 minutes I have time to do it. I'll probably come back to it a little bit tomorrow to just put ourselves back in the mood. So what do we have? We have something like M is of size capital M, N is of size capital N. Well, they're varying over intervals of these lengths. That's what this thing here means. So in an interval of such lengths, we have K of Mn. Okay, and we're going to apply the Poisson summation formula in this heuristic manner. And I'm going to do it with normalization to have this clear idea of what's going on. So what we want is just this sum. I divide by square root of Mn for normalization. And we expect that this looks like 1 over. So I'll start with writing the sum and then putting in the length. So we're going to have h1 and h2. There's only two variables. Each in absolute value have to be less than, well, q over m, q over n respectively. So I did the case k equals 1, but because my variables are independent, I can afford to do it in a similar way, even with two variables. So h1 is up to q over m because m is an interval of length m, q over n for h2. Then I have the Fourier transform of k, which I will compute in a second. And then I have to normalize by 1 over the square root of the new lengths, the product of the new lengths, which will be q squared over mn. Okay, so what is k hat of, I should call them h1, h2, sorry. h1, h2. Well, by normalization, it's 1 over q. There are two variables, so k is equal to 2. Sum over m and n, mod q. E of h1 m plus h2n over q, where mn is congruent to a mod q. Okay, just because that's k was just the characteristic function of this, which I put as summation condition. So this is 1 over q times the sum. So these two variables, m and n, are not independent because they're both co-prime with q because a is. So I can write, let's say, m mod q. So it's a variable that's co-prime with q. And then I have h1m plus h2a. So n is m bar a, where m bar is the inverse of a modulo q, like on Friday. Okay, and I think at least some of you have already seen that in the exercises. This is a sum that's very well known in analytic number theory. This is a Kloosterman sum. So divided by q, so S with parameters h1 and h2a, and with modulus q. Kloosterman sum. Okay, I'll come back to Kloosterman sums in any case a bit tomorrow. Let me now just state the bounds for Kloosterman sums from which the final step of the proof, at least intuitively, can be made. Oops. So it's a deep theorem of André Weil, so that S, A, B, C, for any integers A, B, and C, in modulus is at most the number of divisor functions of C, the common divisor, the greatest common divisor of all three of A, B, and C, times C to the 1/2 for every integers A, B, and C. So what this means is that if there's no common factor, then this is square root cancellation, because the sum has about C terms up to this very small quantity. For instance, if C is prime, this is 2, and this is square root of p, and this is usually just 1. But if, let's say, C is prime, and A and B are both divisible by p, then you get p, okay? Which is a trivial bound anyway. It's a sum of p minus 1 terms of size 1 in any case. So let's take this for granted. I'll come back to this a lot. Now, if you apply this bound here, so the k hat is 1 over q times the Kloosterman sum. So we get, for the sum, the bound so I'm going to pull back the square root of mn that I used in this symmetric expression to the right-hand side, because I just want to understand the sum of km. Then I have square root of mn again from the 1 over q squared times things, divided by q. Then I'm going to sum trivially over h1 and h2, so I will have q squared over mn. And then I get square root cancellation, so if I don't worry about common divisors and so on, I get just square root of q. Okay? And if I did things right, which does not seem so, I have to divide by q. Okay, because my k hat was the Klussmann sum, but divided by q. And now it looks fine. Okay, so. Okay. So that corresponds in the theorem. My second side, the bound for the discrepancy was square root of q times x to the epsilon. The x to the power epsilon will come, for instance, from summing trivially over all the possible sums of this type with m and n. So we know there's about a power of log x such sums, and so on. Okay, so I didn't handle the main term in the sense that I just apply square root cancellation in all cases. So that's a good first step, because if it doesn't work this way, usually there's no chance that it will work with any other tricks, because usually you cannot get better than square root cancellation. It's a very special phenomenon when it happens. And now, if we want to go back and understand where the main term will come from, well, typically it will come when this bound has this greatest common divisor being non-trivial. So maybe I'll say a few more words about that tomorrow. But this gives you an idea, and this is certainly the way to be convinced that the estimate is true, and certainly that this method cannot give better than the theorem I stated at the beginning, because you cannot get better than square root cancellation here. And that tells you what you would need to do. So you would need to handle non-trivially this sum here. Essentially, that's the only place where there's room to try and gain something. It might look like it could be done, but so this theorem is from early 60s, and it has never been improved since then. That's one of the big open problems of analytic number theory, to get an exponent of distribution, strong exponent, or even exponent of distribution stronger than 2/3 for the divisor function. Okay, so I'll continue on tomorrow. Any questions? Yeah.
Can you use these techniques for like the tau k?
Yeah, so you can do, I was going to say a few words about that, but before tomorrow you can try and do it during one of the exercise sessions. So if you do this with tau k, so you should guess that you can get 1/2 is an exponent of distribution for tau 3. And then you can try and see what happens for higher ones. So 1/2, of course, is not beyond Polya-Vinogradov. Beyond Brombier-Vinogradov. But it's critical. It's almost there. So to try and go beyond 1/2, you need to gain a little bit. And it turns out it's possible. So that's why Friedlander and Ivanets were able to go beyond this 1/2 that comes in from a similar analysis. The exponential sums will be different, but if you assume square root cancellation, you'll guess 1/2. And you can do it for tau 4 and the others. I have to think what you get. I made the computation this morning for tau 3, so I know that it's 1/2. I don't remember what you get for tau 4, so guess for the next ones. And you will see there's a problem in that it gets worse and worse. So even if you assume square root cancellation for all exponential sums that come up, for tau 4 it's already strictly less than 1/2. So that means these techniques, I mean for tau 4 we don't know any good exponent of distribution, and that's basically the reason. So we cannot even get to 1/2 with quite powerful estimates for exponential sums. So it's quite, I think it's, well, I would say it's more likely that someone finds a way to handle tau 2 beyond 2/3 than tau 4 beyond 1/2, because the gap is much bigger. Anything else? Okay, then let's have coffee. So James and Dimitris did not dare show up. Maybe they're upstairs? Yeah.